is the same, but I probably won't be able to cover everything that I said I would. So we'll see what happens. We have 25 minutes, 30 minutes?
Yeah, 30 minutes.
Okay, so I'll try my best. So the title is a Baker function for Laplacian growth. So there are lots of experts here on Laplacian growth, but not everyone is an expert, so well, we'll start from the beginning. So a good question, I guess, is what is Laplacian growth? So I have a domain of fluid in 2 dimensions, and I either inject or suck fluid out at a constant rate. I'll call it Q. And we'll take that injection point to be the origin, just for sake of simplicity. Well, the evolution of the boundary of the domain, or the growth or shrinking of the domain, is prescribed by Darcy law. So Darcy law says that the velocity of the boundary, I'll call it Vn, is completely characterized by the pressure gradient. So 2 other equations that kind of go along with this. I need a description of the pressure. So I require the fluid to be incompressible, which means that, well, again, V is 0. And this immediately imposes a constraint on the pressure. That means it has to be a harmonic function, except possibly at the injection point. So there are a couple other assumptions we need to make about, I guess, the pressure. So I need to make some choices about what happens on the boundary, I guess. And really, the only choice I need to make is whether or not I want to include surface tension, and I don't. So we'll ignore it. And well, because I can just choose a gauge, I guess, I have an arbitrary choice of reference potential. I'll just choose the pressure on the boundary to be 0. So in other words, I have 3 equations. This Darcy law. So a little bit more. Too far. This equation for the pressure, and then one more equation for the pressure, which describes how it acts on the boundary. And since we said there's no surface tension, and there's only, well, we can choose the pressure on the boundary to be 0 from, I guess, the surface interface, that's 0. And then again, the Darcy law. So these 2 things say that P is the Green's function of the domain. I should say in omega. So there's some nice complex analysis for you, I guess. And I'll continue with these short comments. Okay. So, right. One more thing I guess I want to say before I continue is what does a solution, or an eventual solution to Laplacian growth end up looking like? And the solution that we're going to, well, what we'll call a solution to Laplacian growth is going to be a sequence of conformal maps from the unit circle into our domain at time t. So F is a collection of conformal maps parameterized by t, and they map the unit disk into our domain at time t, I guess. So this is what F of t does. Okay, I think that's all I wanted to say about that. So one important property that Laplacian growth has is that it's called integrable. So what does integrable mean? Well, there's a misquote of Louis Armstrong that says, if you have to ask what integrability means, you'll never know. So, well, I won't say exactly what I mean by integrability right now, but I'll at least give you a feel. So integrability for us will mean that, well, there will be lots of symmetries in conservation laws, and exploitable symmetries in conservation laws. So we'll actually be able to use this symmetry to come up with explicit solutions. So what is this symmetry? Well, there's this theorem by Richardson. And I'd like to check the year. So the year, I think, is somewhere in the 70s, but 72. So Richardson 72 proved that if I define these things called the moments of the domain, and I'll normalize them a little bit differently than he did, but for a reason. Omega of t, d to the n, dA of z. dA is the Lebesgue area measure. Then it turns out that, well, obviously the 0th moment is the area, and that should change because we're either injecting or sucking fluid out. But the rest of the moments are actually conserved in time. So if, I'll say, omega t, this collection of domains, or equivalently, this collection of functions, is a solution to Laplacian growth, then these moments, dmn dt, is 0 for all n greater than or equal to 1. And for n equals 0, obviously it changes, but it changes linearly. So m0 of t is actually whatever the initial area was, so that's the area at time t equals 0, appropriately normalized, or up to some constants, qt over pi. Okay.
Are you starting off with some given domain?
Yes, so that's an important point, thank you. So I should start off with an initial domain, obviously. I start with an initial domain, omega naught, and then I prescribe the evolution. So think about this numerically, I guess. I start with an initial domain. I compute the Green's function. I evolve infinitesimally in time using Darcy law, and then I recompute the Green's function and continue on. So thank you, good point. So this integrability is very useful because it will actually allow us to compute solutions explicitly. So there's one more formula that we need from Richardson. I think it's in the same paper, but probably someone like Bjorn Gustafsson could tell you better than I could. So this conformal, we can actually write the moments of the domain in terms of this conformal map. So mn of t can be equivalently written as 1 over pi n, the integral over the unit disk. I'll have to notify that. F of z to the n, modulus f prime of z squared, dA of z. And so why is this useful? Well, it turns out two things. So if I write my conformal map as some sort of power series, so I assume it's analytic, z to the n, then I can actually explicitly compute the moments of the domain in terms of these coefficients. And that's probably a theorem that I failed to mention. So if a domain starts out as a domain like this, a polynomial domain, so if I cut off a finite number of terms, it will remain a polynomial domain for all time. So nothing strange happens, and it doesn't at some point become, well, some other kind of domain. Although that's not the case for, say, lemnis gates. So there's a theorem by Dima Kavinson and I think Razvan about how lemnis gates do not survive Laplacian growth. I think that's actually the name of the paper. So the point is I'm trying to make, we can actually compute the moments in terms of these ANs, and we can exploit this to compute solutions exactly. So kind of a simple example. So suppose that, wait, what? Suppose f of z and t is of the form just a1 of t, z. Well, it turns out, if you compute all the moments, you'll find that they're all 0 except for the first one, or for the 0th one, sorry. In the 0th moment, I can write as, well, a1 squared. So using this identity here, I can explicitly compute, well, what m naught of t is. So m naught of t is m naught of 0 plus qt over pi, which means that, well, I guess a1 of t is square root a0 or a1 squared plus qt over pi, with the appropriate sign chosen. And so at the end of the day, this says that well, if I plug this into this expression, what I end up with, this conformal map, is a disk. I start with a disk of some radius, and Laplacian growth will cause the disk to either expand at a constant rate, so the area changes, the total area changes linearly in time, or if I'm sucking fluid out, then it'll shrink at a constant rate. And the same thing is true for, I guess, ellipses. So any other example besides those two will turn out to be too high, sort of bad in some sense. And I'll describe that sense right now. Maybe just with a picture, because if I go into too many words, then it'll be too much. So again, sticking with this idea, I can generate explicit solutions, but some of these explicit solutions have problems. So maybe a solution starts out looking like this. And I keep injecting fluid in, maybe, and it expands. But in finite time, what will happen? So this is maybe t equals 0, t equals 1. But in finite time, I will reach these cusps. And, well, mathematically I have to stop because the evolution doesn't make sense after that. So there are lots of examples for which this happens. It turns out that every known example, at least to my knowledge, this happens in finite time except for the disk and the ellipse. So an important problem, and what I have left to talk about in this next 15 minutes, is, well, how to regularize this problem. So lots of people have done work on this. Lots of people in the audience have done work on this. And initially there were a lot of ideas. So it's sort of a simplistic model. You're missing a lot of things. So viscosity, surface tension, we were very inherently ignoring. But the addition of these things loses this, well, you lose this integrable structure. And for our purposes, we don't want that. So somehow we'd like to regularize the problem while, I guess, preserving the integrability. So, all right, problem. Solutions go to cusps in finite time. And our solution that we're going to try to look for will be to do the following. Try to regularize regularize, in this very vague sense, means try to continue the solution past this critical point while preserving integrability. So. Okay, so here we go. So it's sort of a, well, it's a long story, but it's, well, lots of people have worked on it, and it's sort of an old story. So it's long for that reason, I guess. So the solution will go in 2 steps. Step 1 will be to relate this model to an equilibrium problem. So relate Laplacian growth to an equilibrium problem. And point 2, so after this is done, what we will do is realize this equilibrium problem as a limit of some, well, random matrix model, and we will exploit the integrability of this random matrix model. So it's well known that you can construct an integrable system out of random matrix models. We're going to kind of just take that for granted, I guess. And we'll exploit the integrability of this random matrix model to, well, see what happens for Laplacian growth. So realize equilibrium problem as limit of random matrix model, and step 3 will be to profit. Okay, so step 1, and I have room here, but maybe I should just use a different board. Okay, so first we'll need, well, first I'll need a lemma. So we're working on step 1 right now, so I'll write a 1 here. So the lemma we'll need is something called the Bouillard of Rachmaninoff formula. So I don't actually know who Bouillard is, but Rachmaninoff is at USF right now, so he informed me of this theorem. And well, so he originally proved this in 1999. It's a theorem about equilibrium measures. And he proved it actually only for equilibrium measure support on the real line, but it turns out that it holds generally for any compactly supported domains. And it very generally. So can you guys see? I don't know. I can move it up, or I can just move to that board. So what does the theorem say? So it says, consider the family of equilibrium problems. Minimize U in. So I'll define this class for you in a second. It's a class of measures. Log over Z minus W. So it's logarithmic energy in some external field. So I won't specify the conditions of the external field, but just for our purposes, it fits our context, and it actually happens to be quite general. So I'll define this class of measures for you. So MA of K, maybe I'll call it T is probably better for right now. I'll use A later. So MT of K is a class of Borel measures, positive Borel measures, compactly supported in K with total mass T. So consider this family of equilibrium measures. And, well, equilibrium problems, I guess. And call the minimizer with fixed value T. How about lambda T is solution for T. So the BR-Rachmaninoff formula tells you how to differentiate this measure and what the result is. So all right, then d lambda T dt is nu of the support of lambda T. So I'll tell you what this means. If I differentiate this equilibrium measure with respect to the total mass, what I get is the equilibrium measure of the support of the measure of lambda T. So equilibrium measure means equilibrium measure in no external field. So we'll need this shortly, and maybe this will be the last thing I say because, well, the last thing I prove, because I know running short on time. But that was expected, so you do. Okay. So next, well, we're going to connect, well, our Laplacian growth problem to an equilibrium problem, and we're going to do that through. Yeah, okay. So use of, well, a measure that characterizes our domain. So if omega t is a solution, so I'm going to interchangeably use this notation and the notation that the sequence of functions are well, solutions to the Laplacian growth problem. So let this be a solution to Laplacian growth problem. We will associate to each of these a measure. So I'll write this. So this is characteristic function of the domain multiplied by the area measure. So it's just area measure restricted to that domain. And it has total mass, whatever the area of the domain happens to be. Okay, so essentially we're going to come up with a formula for differentiating this object with respect to t. So yes, okay. So we know from the Richards and moment formula that all of these domains, except for, well, all of the domains have the same moments. So I can associate to them this family of moments, except for, of course, the first one. And we're going to assume, just for sake of time, that there are only finitely many moments. This is like a, well, you can actually prove this is a polynomial domain. So the boundary curve is described by a polynomial. Okay, and the equilibrium problem I can actually associate to these numbers and these domains is going to be the following one. So theorem. Tk d to the k plus tk bar z bar to the k plus modulus z squared du. So this problem, again, computed in the class of measures with total mass, whatever the area of the domain happens to be. So area of omega naught to area of omega naught plus t. We'll solve the Laplacian growth problem. How are we going to show this? Well, it takes a little bit of work. So maybe I'll just skip that for right now and tell you a little bit more about where this is heading. So we really didn't get to use Boyar-Rachmaninoff formula, which I kind of wanted to do that proof. There's an interesting, although it's probably known to someone, proof of the fact that this equilibrium problem is related to, Laplacian growth via this nice formula. But if you're interested, we can talk later. Okay, so we have this equilibrium problem now established. We kind of skipped some details, but there's only 30 minutes, so you do.
What's the statement?
So the statement is that the minimizer, or the family of minimizers, over the class of measures. So M, I'll denote area of omega naught, or of omega naught by A. So A is area of omega naught, A plus T, over some sufficiently large disk that contains all of the domains. So we have at least compact support. Will be the family of measures, these things. So chi omega t dA. This is a classical result, but yes, Einstein summation convention. So k equals 1 to n. Thanks. Yes, so this is the statement that you actually end up with this as the minimizer. So we've now converted, the point is that we've now converted this Laplacian growth problem, which was a PDE, into an equilibrium problem, which is useful because we will now be able to convert it further into a limit of random matrix model. And for those familiar with the, technique, it's not such a big step to kind of figure out how to do this. So I'll sort of just write down the random matrix model. But it's a well-known technique how to, if you're given an equilibrium problem like this, there's an intuition, behind how to actually construct the random matrix model. Although maybe the matrix model in question may be, not immediately clear. So I'll just write one more theorem. And probably I would associate this to Felder, and their paper is from 20-something. 2013 sounds too late, but it was 2013. Okay, so Felder 2013. 2013, not 1913. So it says that this random matrix model. So consider the normal matrix model. So normal matrix model means the class of normal matrices, the ones that do this with partition function. Essentially given by T vector. The external field. So e to the minus n trace m dagger m minus, I think that should be a minus sign, but dk, z to the k, dm. And so the area measure on this space of things. So their theorem says that essentially the scaling limit of the free energy is the minimizer, or is, I guess, yeah, the solution to the equilibrium problem, I'll say. Equilibrium problem. And I'm kind of going over your time now, but so the point of the talk was going to be that if you look at the Baker function, what would be called the Baker function for this hierarchy. So here, in the case of, if you don't know what a Baker function is, doesn't matter. You look at the orthogonal polynomials associated with this partition function. If I integrate out eigenvalue variables, I end up with something like Vandermonde in Z1 through Zn squared, and then this external field part. What was I saying? So if I look at these orthogonal polynomials and then I send limit n goes to infinity, well, I end up with what would be the Baker function for this integrable system. And the point would be that it has knowledge about well, when these cusps develop. So I'm kind of going over time. So I'll.
You've got a couple more minutes.
I have a couple more minutes? Okay. So I have too many pages and I don't know what to say. So let's see. Maybe I'll say a little bit more about well, this problem and how it connects to these orthogonal polynomials. So I can rewrite the partition function after I integrate out eigenvalue variables as integration over Cn, Vandermonde squared, e to the minus summation modulus zk squared minus some tk. K is a bad letter now. J. Zk to the j. J equals 1 to n. N is a bad variable too. So, well, if I rewrite this, Vandermonde determinant, we all know, is this thing. So if I rewrite this as x log of summation, or summation of logs, do I want to do that? No. So here's the, it's too high up. So this term, I can, by just adding to the columns, it's a determinant of Ci to the k on I and k. So I can, just by adding to the columns, create polynomials of whatever I choose. And I might as well just choose them to be orthogonal with respect to this measure. But an issue that arises is that the orthogonality of these polynomials is Hermitian, and well, e to the blank. So Hermitian orthogonality is very nice for people that don't do orthogonal polynomials. For people that do, it's not so nice because you lose a lot of nice properties of these orthogonal polynomials. So the problem is not as straightforward as, well, if anyone has worked in Hermitian random matrix theory. It's not as straightforward as Hermitian random matrix theory because you can no longer use things like the three-term recurrence relation to get asymptotics. And if you want to try to set up a Riemann-Hilbert problem for these orthogonal polynomials, that's even a little bit harder because, well, what's the contour of orthogonality? You don't have one, at least not immediately. So there are extra issues that arise. And maybe that's all I'll say for right now. So if you want to hear more, we can talk later. But I know you guys probably want to go home. So I'll stop there. This one?
Yeah, this one with the cap. So this, you think of swelling fluid domain.
It can either be swelling. There's an equivalent problem where it's yes, but it can also be suction. Suction also leads to these cusps.
What did you choose? You must choose.
So
That picture is not quite right. You have to suck inside. You get the
okay, so
Yeah, so if you have injection, it will become smoother and smoother, and you never get.
true. So bad picture. Sorry.
But this kind of picture you used to get if you suck fluid from the point of infinity.
Yeah.
Another question is, worried about your definition of movements, because you have an n.
At the end, yes.
The denomination is
So it doesn't affect. Obviously, if I add an n, it doesn't affect the conservation.
yeah, but if n equals 0, it's not a very.
So that's a good point. Yeah. So for n equals 0, it's just defined as the usual area. I should comment on that. But the reason for the normalization is so that well, this ends up as tk z to the k, t bar k, z bar to the k, as opposed to having to divide by k every time. So just a normalization. Yes.
I must have missed something very basic. You have a boundary defined by polynomial.
This. So it turns out that things like this come from not polynomial curves, but well, I think Elbow and Felder still call them polynomial curves, but they come from curves with the form. That's true. That's a good question. I'll have to think. You know, if I have polynomial curve,
So it's a matter of whether Q is positive or negative. When Q is negative, then you get cusp. When you have polynomials, the derivative of the conformal map which will become 0. And that's almost that generic. You run into cusp.
I didn't hear that, and I didn't understand.
I think what you mean, like, a polynomial curve, the conformal mapping from a disk is polynomial.
yes, yes. Yes.
There are polynomials that come in from different directions. One is related to the conformal map, and then he gets these moments, and those moments are related to orthogonal polynomial. Those polynomials have nothing to do with the conformal map directly.
Yeah. So these polynomials and those polynomials are unrelated. The ones I'm talking about over here, just parameterize the conformal map, whereas those come from a regularization of the problem.
I can also make a comment. I remember from time when I also was involved in, I think it's like you need to solve an inverse problem, but it's very hard. So you describe the conformal map, and then you end up with this task. But if you find non-integrable some sense domain, it may not go. But it's not solvable.
Yeah. So no one knows how to. I mean, it's
Way to solve it.
if you start with a generic domain, there's no way to know what happens. I think is that your point?
Those examples that are integrable, then because it's hard.
Yeah.
But it doesn't mean that they're always.
No, it doesn't. And I think it's an open problem. Yeah.
Or maybe it's
It's very possible that it could be.
not so physical.
Yeah. So there could be some domain for which it expands for all time and everything is very nice, but no one has come up with an example to date. So
So you mentioned that this is a regularization approach.
yes.
I wonder what sorts of the regularization parameters such that the usual problem is recovered once the parameter goes to 0.
So the regularization is via this discretization. It's so there's an analogy that Krejcir gives to KdV0 dispersion. Probably the dispersion parameter is well, I guess n, and then the regularization is when I take the scaling limit. So that's I guess the parameter.
So it's kind of like a mathematical regularization. You're making an analogy, which in the limits is
Yeah.
this physical problem, but then you're going to let n be finite and large.
Yeah, and it turns out that actually, so another direction the story takes, this problem itself, so the discrete problem shows up in condensed matter theory as a growth problem for electronic droplet for quantum Hall effect. There's a paper by Wigman, Zabrodin, and some other people that discuss this. So in the sense of that, it's the more interesting problem for them. And Laplacian growth is the end story. It's just, I guess, the effective field theory, or the effective theory, I guess. Yes?
For very different reasons, the Q negatives problem is not physical.
Okay.
Even before any cusp form, if you put in any regularization, the regularization effect can precede even the cusp formation. So you have a singular effects even when the surface is smooth.
Okay.
So therefore, if you put in surface tension or other kind of regularization, it doesn't, that Q negative problem, though mathematically is beautiful,
It's just
not
bad, yeah?
physical. It's not physical.
Okay.
Q positive is certainly physical.
Yeah. We'll have to talk more later. I'm interested to hear.
Yes, by the way, Sally wrote a very nice review article on this called Surprises in Viscous Fingering, which is well worth a read.
Okay.
Thank you very much, Nathan.
All right.
Let's close the day.